Perfect. Hello, Gabe.
Oh.
All right.
Feel better.
Chapter 3, derivatives. It is what it is. I mean, I check attendance every day anyway, so. I check attendance anyway. What? Okay. Chapter 3, derivatives. Here we go, derivatives. So, in 2.4, we learned how to derive the formula for the slope of a tangent and arbitrary point. So, if you have your 2.4 notes, like this is literally the end. In example number 4a, we found the slope at an arbitrary point. So, we found the slope at a comma 1 over a. On the graph of the function, f of x equals 1 over x. And we showed that the slope would be negative 1 over a squared. Because remember our arbitrary point, instead of picking like, oh, at x equals 2. No, we said when x equals a. And if f of x was 1 over x, guess what y would be? Oh, the y, f of a, is literally going to be 1 over a. That's how we found this point. If we want the slope there, we plugged it into the tangent equation. Remember the tangent equation where it's like f of x plus a minus, I'm sorry, I forgot we have h. X plus h minus f of x all over h. And of course, this is the limit as h approaches 0. So this is how we found the slope of a tangent. So if we're using those points, this is back in 2.4, which is like forever ago, a week ago. We found the equation was 1 over a squared. So this result is actually way more interesting than you had any clue. It's because it's a simple way to calculate instantaneous rate of change at any point, right? This whole thing, remember when we did limit as h goes to 0, that whole thing, I just wrote out for you. This is instantaneous rate of change. I can find the slope at any point. So the study of rates of change, a function is called differential calculus. So differential is telling you what differences what the difference is, how things are changing with respect to something, differential calculus. And this formula, negative 1 over a squared, was your first look at a derivative. Right? So what you can think of a derivative is literally the slope of a tangent. Right? So it's your rate of change. So your derivative is your rate of change. So normally we've thought of like slope as rate of change. And in math, for the most part, we've learned how slope, we really talk about like straight lines with slopes. But what if we have like other functions, like real life things, like, x to the 5th, and like these other functions that are not linear? Well, we could find our rate of change at any point. We could find a whole function that will be my derivative. Elliot, sit up. All right, and just remember, right, slope of a tangent was that whole function we did up above. And just review a little bit. The average rate of change, that's your secant line, and that's when you have like f of b minus f of a over b minus a.
What's the difference between the average rate of change and the...
Instantaneous?
Oh, never mind. I understand.
It's the difference between when you're driving to Vegas and you are going an average of 60 miles per hour. But that's not true when you're driving through LA. Right? Because if you look at your speedometer, your instantaneous, you could be going like 0 because people are stupid and don't know how to drive. Yeah. Drove by a car this weekend where it was literally burned out. Like these two cars got in such a bad wreck. It was just ash.
Ew.
Yeah, I'm like that. Yeah, that's sad. Always wear a seat buckle. Okay. Throw that in whenever I can. Notation. So there's many ways to note the derivative. We can write the derivative many different ways. The first one is f prime of x. So it's this little like apostrophe looking thing.
This is new.
Yes. Yes. Welcome. Welcome to newness.
Thank you.
Yes. So we say this is f prime of x. You can also write it as like f prime, which reminds me of the next one underneath, y prime. So y prime doesn't tell you what the independent variable is. Unlike the first one where it's f prime of x, x is going to be my variable that's changing. If I just have y prime, maybe Maybe my equation has t in it or something, right? So it's not, I mean, it's useful, but these all mean the same thing. That's what I want you to notice. These all mean the same thing, just different ways to say the derivative of y. Derivative of f of x, derivative of my function. All right, dy dx, you can also say this one as the derivative of y with respect to x. So notice the bottom is what it's with respect to. You also could say df dx. You could say the derivative of f with respect to x. So this like shows you what I write versus how I say it. That way you're like, what do you mean when you say y prime? Oh, literally it's going to be y prime. When I say dy dx, dy dx, this is the dependent, independent. All right, and d dx of f x, or you can say the derivative of f of x. Literally all of these, you're always looking at f of x. And then, okay, so I guess an example is, so an example, if I have f of x and it's equal to x squared, I could say f prime of x is equal to 2x. You don't know how I found that yet. Maybe you do. I don't know. But I'm showing you the difference. When I write the original function versus the derivative of my original function. So you notice the derivative has that prime mark in it. Okay, cool. Fun fact, if I want the second derivative, guess how many prime marks I do? 2. Aha.
Wait, what's the second?
It means it's the rate of change of your rate of change.
How do you even do that?
Who's taking physics?
Hey.
Who's in physics?
In?
Or have taken it?
Let's say OG.
We never did really done that.
OG function.
OG function?
Yeah, the original function?
Oh.
Okay, that's not a math term, whatever.
No, I understand.
Okay,
You teach physics for surprise?
that's a shame.
What?
I did. I like secretly taught people physics when I was teaching physics. Yeah, I secretly taught derivatives when I was teaching physics. All right, definition of derivative. Is this familiar? One more time. One more time. Is this familiar? Yes. Yes, it's familiar. Yep, we did. The definition of derivative. It's like there's gradual steps, and I'm like walking you through so you understand it. Man, it's like this was planned out. The derivative of the function f with respect to the variable x is the function f prime, whose value of x is. So wait, what you're telling me is the derivative is literally the equation I get from the tangent function, from the tangent, right, with the limit. So what you see is derivatives are limits.
Oh, so it's just another name for what we were doing?
Yep. Trick play. Got it. Got you to learn it without having to tell you what I was doing. Derivatives are limits. So provided that the limit exists. Remember how we went through different places where the limit doesn't exist?
So would there be no derivative?
Exactly. Oh my gosh. So if the limit doesn't exist, we can't have a derivative there. Okay. So if the derivative exists, we say f has a derivative. It is differentiable. We can take the derivative. If something's differentiable, that means we can take a derivative. A function that is differentiable at every point is a differentiable function. So as long as there's no holes, as long as there's no points where my limit doesn't exist, that means there'll be no points that also don't have a derivative. So if I am fully like differentiable, that means I could put any point in for my x value into that little tangent function right here, right there, right? And if the limit exists at every single point, guess what? I can find a derivative at every single point. And if I find a derivative at every point, I can say the function is differentiable. Okay. So that's a lot of words. So let's differentiate, aka find the derivative of f of x at x equals 3. Sorry, Tal, you had a question? Then it's not differentiable at that point. right? Then it won't be, well, it won't be differentiable at the point, well, the whole, so having a whole is a little different. Yeah, we'll go through these. All right, so differentiate, find the derivative of f of x equals x cubed. So what we want to do is I want the derivative, so f prime of x, that's going to be equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So what we're trying to do is we're trying to find an equation, not just the slope at one point. I want the slope of my original function at every point. I want to find an equation that'll tell me the slope of my original equation at every point. Okay, I think I've said it about 50 times. We're good. All right, so first I'm going to plug in. Let's see. So I have to plug these into my original function. Oh no, I think my storage only has 50 minutes left.
What?
Yeah. My computer's running out of storage. I'm doing too many screencasts. They're important. All right, so x plus h cubed minus x cubed all over h. Do we remember how to do x plus h cubed?
Yes, but yes, it is you just do x cubed plus 3x plus x cubed. No. There's like x cubed plus
No.
6x. You just do it squared first and then you just
That's exactly what I'm doing. X squared plus 2xh plus xh squared. Multiply that by x plus h. So you have x cubed plus 2x squared h plus xh squared plus hx cubed plus 2x h squared plus h cubed. Is there anything I can combine these? And I can combine, so I'm drawing different squigglies to show you the combining like terms. Cool. Okay, so I'm going to rewrite my line.
Yeah, how can you combine?
So one is a solid line, I'm showing you I can combine those, and the other is a squiggly, I can combine the ones.
Oh, you can do it.
Yes. Yeah, because x squared h is the same as hx squared. Okay, so I have plus 3 x squared h plus 3 x h squared plus h cubed all over h. And don't forget to bring down your minus x cubed term from the previous one. Okay, so someone shouted out already. They said that crosses out. It's true. Awesome. Exactly. So hopefully you see by now there is a pattern emerging.
Don't be minus. I'll be a minus.
Right here, from right here, I had to bring it down.
Well, right.
No, it's all cool. Like, it's very easy to lose track of where you are. Okay, so I crossed out my x cubed. Notice that every single term has h in it. Okay. So alternatively, I could have pulled out an h and then I could cross it out. I don't know if that'll help you or not. Help you see it a little better. So I have 3x squared plus 3xh plus h. And guess what happens? As h goes to 0, as those go to 0, this is just going to equal 3x squared.
Isn't it plus h squared? So h squared, h cubed. No, so then it's h squared. I mean, it's still 0 though.
Still goes 0. But you're right. Thank you. Yeah. No, thank you. Okay. So what we found was the derivative. This equation right here, if you pick any value of x for your original equation, I can tell you exactly what the slope will be at that point of the tangent. Well, pick a number, Maya. Any number. Go.
37.7.
Why? What? Oh my god.
I was under pressure.
37.7. Okay, so if you if you graph x cubed, and you go to where it is 37.7, all the way up there, I can tell you what the slope of the tangent line would be. It would be, well, whatever 37.7 squared is times 3. That's what the slope of the equation is. Yeah? Questions? I want to keep going. Questions? Oh, I don't care what it is. All right, cool. No questions? We keep going. Perfect. You just found the first time you knew it was going to be a derivative, that's what you found. So what you notice is, okay, this is getting a little ahead of myself, but I want you to see it. If I would graph x cubed, it looks like that, right? Well, it goes through the origin though. Looks something like this. If I'd graph my derivative function, it's in pink. What do you notice about the degree? Well, I start with a third degree and I end with a second, so it's one less. Derivative is one less degree. Okay, whatever. We'll come back to that.
Derivative is one less degree.
Yeah, so since I had an x cubed function,
Oh my god.
yep, I'm planting the seeds so later I can actually harvest the crop. Okay, it's probably the most Nebraska thing I've said all year. Example 2. Example 2. Use the definition. So use the definition of a derivative to find the derivative at the indicated point. So when you have the x value, you should get a number as a result. So when I don't give you the x value, for example 1, we found the derivative equation. Found the equation for the slope at any point. But when I give you a point, we're going to find a number. We're going to find the slope at that point. Maybe I should write that. When you have the x value, you should get a number as a result. Number as a result. Okay, so notice we are finding it at a point. A equals 2. So what I need to find is f prime of 2. I want the derivative at my x value of 2. So I'm plugging in. So I have the limit as, yes, because if you don't write the prime, that'll be the function. It won't be the derivative of the function.
But could we technically write any of these things?
You could say,
Y prime?
you could say dy dx.
Oh yeah, no, I might not.
So that's how you would write, yeah.
Yeah, I like that.
When you have the x value, you should get a number as a result. Okay, so limit as h approaches 0 of f of 2 plus h. Why am I using 2? That's the point. That's the point I'm given. That's the x value. I'm plugging 2 in for x.
Why do you use x instead of a? Because
Well, because in the equation it's a plus h minus f of a.
No, but I'm saying here's x, but in the other
Yeah.
lesson you taught us a. Does it matter? Okay.
It's, I mean, the book you look at, the calculus book you look at, even on this single page, the difference between, if you look at the top of the page, where I have x in here, and then down here I have a, it's the same thing. But here, a is literally when you have the x, it's oh, you're going to find an equation for the end. When you have an a, it's oh, hey, I gave you a point to use. That's really what the difference is, but I'm trying not to tell you too many things. So, same. Okay, so we're going to plug this into the equation. The equation is x squared plus 3. So this is going to be, and you do have to write limit every time. Okay, cool. Grouping symbols are your friends. Use parentheses. So I have 2 plus h squared plus 3 minus 2 squared plus 3. Do you know why I'm telling you to use grouping symbols? Because you might forget to distribute the minus sign. Oh my gosh. Yep.
Oh, I know.
Okay, so I have 4 plus 4h plus h squared plus 3 minus 4 minus 3 all over h. So I did the 2 plus h times 2 plus h. You see the 3's go away, the 4's go away. For h plus h squared all over h. So we found a number. We found a number. Guess what? Let me zoom out a little bit.
So you know if you don't get a number that you did something wrong.
Yep. Whenever you have an x value, you should get a number as a result. Therefore, f prime of 2 equals 4. And just so you know, those 3 symbols means therefore.
What was your hair?
Yeah, Mr. Pierce.
It was off.
Oh, IE. Wait, how does IE translate to for example?
Don't worry about it. That's not. I'm. Why don't you ask me now? No, ask me that question later. Goodbye. Okay.
Last year he wrote IE on the board and said what and he said for example, and for a whole year I've been trying to figure out how.
I'm a little confused. I thought this was math class, not Gossipville. Okay. Whatever. Okay. Literally, IE, QED. He's not even listening. Noah, QED is also one. IE. Look in the Latin. QED. It means like end. Look it up. It's Latin. IE is probably
It's Latin also.
Like a
Yeah.
British
It's informis exemplis.
yeah. So for example, if you even Google IE, it will tell you that. Okay.
That takes a little bit of
Yeah. All right, we're gonna continue. Shh. Guys, today is 3.1, not tomorrow, not the day after, not the next class is 3.2. Let's continue on. I don't mind pausing if we have an actual question about what we're doing here. Okay. So the definition. It's the alternative definition of a derivative at a point. So the derivative of a function f at a point x equals a is the limit as x approaches a of f of x minus f of a all over x minus a. This is a second way of writing derivative. Notice there's no h, right? So this is actually the same thing. Just imagine, so imagine that, no, I don't want to confuse you too much. Okay, this is the same thing. This is also how you find derivative at a point. F of x minus f of a over x minus a. And this is as x gets closer to a. Because guess what happens if x equals a? It's 0, divided by 0. It would be indeterminate. 0 over 0 wouldn't work. So as it gets arbitrarily close, as we get really, really close. So before, we were letting h be the difference between my 2 points. Here, we just got rid of the h. And we said, okay, you know what? Let's look at my 2 points. And as my second points get closer and closer to my first one, well, as the second point turns into the first one, as it gets close enough, it's the same number. What is the limit? What is the slope? So we're going to use this second definition to find the derivative of the given function at the indicated point.
I have a question. Are
Yes.
these formulas different?
This is actually the same formula, but it's just written differently. Yeah.
Can we just remember one formula and just one formula? Or
You need to know both.
Sure, we'll-
You need to know both.
How you've written? I have a question.
Yep.
How come we didn't use this one for this?
I don't know what you're looking at right now.
Like the last problem one for a equals 2. How come we didn't use this?
So,
Like, how do you know when to use this or when to use the x plus 2?
yeah, so I'm hoping by doing the examples, you guys will come up with that by yourself, because me telling you will mean nothing if you have no idea what we're doing. So ideally, we'll go through these examples and be like, I got it. All right, so I have this one. I have the function square root of x minus 1. I want to find the derivative at my point at x equals 2. Here I have a equals 2, because up in the equation, everywhere there's an a, you would plug in 2. So f prime of 2 is going to equal the limit as x approaches 2. So that's just whatever value you're getting close to. And then we have f of x minus f of 2 all over x minus 2. So I wrote it out explicitly here, so that way I could go not lose you as I plug it into my function value. So square root of x minus 1 minus square root of 2 minus 1 all over x minus 2. So if I want to rewrite this, make it a little easier to read, I have square root of x minus 1 minus 1 all over x minus 2. So this is an issue. I have a square root value. How can I get rid of a square root? So this is, well, let me put it this way. Throw back to when we were in chapter 12 last year in pre-calculus. If I would plug in 2 in for x, I would get 1 minus 1 on top and 2 minus 2 on bottom. I'm getting an indeterminate form. How did we deal with limits like this? When we had square roots, how did we deal with them? So this is literally just like a problem we did last year in chapter 12. We're taking a limit. If you plug in x equals 2, you get 0 over 0. It's indeterminate. How do you deal with indeterminate forms? Ty. Multiply the top and bottom by the
conjugate.
Thank you. Conjugate. We're going to multiply by the conjugate. That's the word I was waiting for. So we're multiplying by the conjugate. This is literally, oh my God.
X plus 2.
I see a common thread. I see
it's
next time, like, you're forever moved over here now.
What?
No, like this is I'm done. You're moving over here after today. Okay. Because then if you have questions, you can ask me, but then I don't see you turn around and talk to Maya. Okay, so I'm multiplying by the conjugate, which is square root of x minus 1 plus 1 over square root of x minus 1 plus 1. Well, so this is one route we took to solve indeterminate form when we're taking limits. Yeah, because I'm just multiplying by 1. What I have in pink is literally 1. I'm multiplying by a clever form of 1. Okay. So by the conjugate, so this is more or less a difference of squares. So you take these, and you multiply, and you take those, and multiply them together. So it turns into x minus 1 minus 1 over, and then I have this whole nastiness, x minus 2 times square root x minus 1 plus 1. Okay, so this is literally the same thing. The top goes to x minus 2. Oh, interesting. Notice what happens on the bottom. Yep. So really hope you guys didn't throw away your pre-cal notes from last year. So this is probably like if you're in my class last year. Because we did this. Bring them out. Look at them. Okay. This is 12. Chapter 12. Actually, chapter 4 as well. Is it 4? No. 3? Something. I remember doing it with the seniors as well. That he was a senior last year. All right.
Why do you only think of it?
Okay, so I have the limit as x goes to 2. So I'm going nice and slow, so we won't have any questions about the algebra I'm doing. Square root of x plus 1 plus 1. Wait, now if I plug in a number.
Minus 1.
Minus 1. No, it's not.
Yeah, in the inside of the root.
Oh, yeah, thanks.
Oh, then
Now you just plug it.
So if I plug in the values,
Stop.
1 over root 2 minus 1 plus 1. So that's 1 over 1 plus 1. So that's 1/2.
Jesus, that's like a nice
It. Love that. Love that. Yes.
Yeah. Okay. All right. So pause here. Do you have questions of the process? How we did this? Multiply by the conjugate. It's a nice little tool. Okay. Let's try the next one. Do we need more time to write this down?
Wait, why do you wait so long to plug in?
Because if I would plug in, I tried plugging in 2 at this point right here. No, wait, hold on. Right here. Tried plugging it in right here, and I got an indeterminate form.
Oh, so this is the thing where sometimes it works with that one step.
So originally, like, if I could just plug in 2 and it would work, I would be done. But I couldn't. The whole reason I had to multiply by the conjugate is because I got indeterminate form. When we have indeterminate form, there's like 3 different things we do. One of them is multiply by the conjugate. Another is we check if anything cancels out, any factors. Maybe we had a hole there. Yeah. I don't think you guys realize how important that chapter was. Cool. Okay, let's keep going. Find d dx of 3x squared. What this means is, guess what? Find the derivative. We're finding a derivative when x equals -1. Okay, so I'm going, So, I'm finding the limit as x approaches -1. And I'm going to take, let's see, f of x. So f of x is just 3x squared minus f of a all over x minus a. Is that too big of a step to take? Maybe. I don't know. I don't know. I said it out loud. Okay. I just straight up, instead of, I will write it anyway. Okay. Just in case you're lost. This is if you're lost. You're like, what should you do? Except where I had an a, I put a -1. Oh my gosh. And I plug into the equation. That's so you see where I did. All right. So I have 3x squared. -1 squared is 1. So minus 3 all over x plus 1. If I put in a -1, I get indeterminate form. Ooh, indeterminate form. Right here. Right here. I'm trying to plug in -1. I get indeterminate. So.
Is that the 0? What is the 0?
0 over 0. 0 over 0 is indeterminate. If I try plugging in my x value, I get indeterminate form. So here's another key. Okay, so multiplying by the conjugate is one tool. What's another tool? Factoring. Oh my gosh. Okay, let's try factoring out. Let's see what happens. It feels good when you know what you're doing. It feels good when you know what you're doing. So I have 3 times x squared minus 1 over x plus 1. Oh my gosh, x squared minus 1 is a
perfect square.
Difference of squares. Okay. You recognize it. Okay, so 3 times x plus 1 times x minus 1 over x plus 1. Oh, that's a different color. Oh my gosh. Of 3 times x minus 1. So now if I try plugging it in, I will get a number and it will work out and I'll be all good. So, -6, correct? So if you want to write it, you could say dx of 3x squared, evaluating it at x equals -1 is equal to -6. So this is like saying.
Do we need to write it like that? It's a little extra. What?
Okay, I'll explain it again. d dx of this function. Find the derivative of this function where, at x equals -1. It's equal to -6. You know, you ask me these questions. I'm not 500 years old. Like, I didn't make this up. This is what was passed on to me, you know?
Yeah.
This is the way they decide to write it. Like, why is M look like an M? Like, I don't know. That's the way they decided to do it. This is the way they decided to do it. This is the notation. And I'm explaining the proper notation. Your opinion, cool. Okay, but
It doesn't matter.
Do that together.
what?
Is that just a notation for A? Is that just F1? What's it called? F1?
I mean, okay, you want to write the notation at the top.
Which one do you prefer?
F prime 1 to 2. Is it F prime of 2? You just write equals negative.
So for this first one, f prime of 2 equals 1/2.
Like on the test, when there's the little line.
Okay,
you just do
hold on, pause. Did I say you had to write this way? No, I didn't say that. What I said was what it means. So if you look at it in your book, you're like, oh, I got it. I don't like just show you the easy way, and then you go to college and you take calculus, you're like, what the heck is this? Oh, that's right, I showed you. That were these little seeds of knowledge planted, and you're like, okay, I saw it before. You're okay with it. It's not just like brand new. I'm showing you what it means. I'm teaching you what it means. Whatever. Okay.
Wait, because we're like for seniors, we're only taking A now.
Huh?
We have to retake this in college.
What?
Because we're only taking
Well, a lot of colleges will
we have to take like
test you. Will make you take a practice test. Make you take a placement test. I think you guys, most colleges, I think, have single variable calculus as 2 classes. So I don't know how. Depends what you're studying. All right, we do have 2 more minutes. That's enough for this because this one's not too hard. Okay. So to be really on the ball next time, just make sure. No, we got 2 more minutes. Relationships between the graphs of f prime and f. Because we can think.
Oh no.
It's the tennis.
But like, if these break, we're going to buy new ones.
They're like $1,000 each.
We have a thing called a budget.
What are those, by the way, out of curiosity?
I want to say a whole setup is a couple $100.
But like the one, like if you want to buy one half.
You can't. You have to buy a set.
Why would you only want one?
Oh, yeah, just keep it.
Okay.
Why would you need it?
Guys.
Yeah, like, why would you want one? Half calculator. Why would you? What's better with that?
Okay. So, how many pages are in 2? 1, 2, 3, 4, 5. So you have to be on the ball next time. You guys have to be on the ball next time. I'm expecting you when you come to class tomorrow. No, we don't have class tomorrow.
Oh yeah.
Wednesday.
Thursday. We don't have class. Thursday, we have 6.5 pages to go over. What this means is, I'm not going to put up with any of your little ball honky. I'm letting you know right now, I'm not putting up with your baloney on Thursday. You don't pay attention, you get doc participation, goodbye. We're going to go through the notes. All right, you have questions, raise your hands, but like it shouldn't take this long to do everything.
I have a dentist appointment.